Okay, now we're going to be talking about where a function is what they call differentiable. And I abbreviate this differentiable. I'll often write something like this, diffable, just because differentiable is like too long to write. So we're going to be looking at where functions are differentiable, and I've shown you my abbreviation, but let's talk about where a function is not differentiable. So let's suppose that I have some function and I'm going to say it's discontinuous at some number x equals c. What does that look like? Well, let's say it looks like this. I think you've seen these before, all right? So it looks like this, and I'm going to put a little dotted line here. This represents c, all right? That's the point c where there you see like a jump, all right? So let's call this a jump. It's discontinuous here. It jumps from one point to another. Notice that's open, and that one is solid. Okay, so right here we cannot take the derivative at the point C because there's a discontinuity. It has to be smooth. It has to be continuous. When you draw the graph, you shouldn't lift your pencil, in other words. So that right there, not discontinuous at the number C. Or it's not differentiable, I should say, because it's discontinuous. What about here? Yeah, you could take the derivative there. You could take the derivative there. You cannot take the derivative at the number C. All right. So let's see here. What about this right here? If I draw this graph here, and I'm looking at this point here, call it C. That's what they call a cusp or a corner. I'll also write in corner, cusp or corner. So at this little point here, that tip there, you cannot take the derivative. All right. Notice this function is continuous, but it's not differentiable everywhere. So continuity, because the function is continuous, does not imply differentiability, but differentiability does imply continuity. It goes the other way around, right? So right there, we call it a cusp or a corner, all right? That definitely does happen. Think about like an absolute value graph. That could occur, all right? Now, the last case is the case of the vertical tangent. And you must be wondering, what the heck is a vertical tangent? Let me see if I can draw a better picture. All right, let's say I have this function that kind of goes something like that. Well, suppose here where it's kind of just shoots straight up, we'll call that a vertical tangent. Well, why the heck is it not differentiable? Well, think about what a derivative is. It's the slope of a tangent. What can you tell me about the slope of a vertical line? The slope is undefined. Therefore, the derivative is undefined. Okay, so this right here is what we call the case of the vertical tangent. Okay, so kind of keep that in mind. All right. Okay, let's take a look at some examples. Here we're going to draw some graphs, but they're really easy graphs. So I'm just going to sketch them roughly. And I am not an artist, and I don't claim to be one. I'm the guy that draws a crooked line with a ruler. So let's say we're investigating the graph of f of x equal 1 over x minus 3. You can use your calculator, I suppose, but I don't think you really need one. All right, we know it's this function, a rational function with an asymptote right there. Looks something like that. That's one part of it. Here's the other part of it. Okay. All right. There you go. The question is, you graph it and then state where it is not differentiable. Now, you may have assignment questions similar to this. I don't know. But take a look at this one. Where is it not differentiable? Well, clearly at 3, right? It's discontinuous. Why? It's got an asymptote. So I'm going to write in here that it is not differentiable I always put diffable just to abbreviate it, makes it shorter. At x equals 3. Why? Because it has an asymptote. Plain and dry. All right, let's take a look at the next one. Here's another graph. This one is the function f of x equal absolute value of x plus 2. So we have a number here, call it -2. It's this kind of V-shaped graph. All right, I tried my best. All right, I really did. So where is it not differentiable? Well, here we're going to say it is not differentiable at x equals -2. Why? It's got this kind of a cusp. We might also call it a corner. So there's our justification there. All right. Now, there's another graph. Suppose that I had, and I'm going to make this example 2a, I guess. Let's say I had this function y equal x squared, a parabola. All right. Well, where would it not be differentiable? Interesting. This one is actually differentiable everywhere. So it's possible for any polynomial, really, because we know they're all continuous. Any polynomial, they're differentiable everywhere. Okay? But kind of keep this in mind here. I mean, it's not too bad. So that's a possibility. If you get a question that asks, where is it not differentiable? Well, if it looks smooth, continuous, no cusp, no vertical tangent, then this may be the answer. It could be a trick question. So keep that in mind. All right, let's take a look at example number 3, and we'll look at some other quick examples here. This isn't too bad. So this graph here is the graph of 4 times the cube root of x. And again, I'm not an artist. I don't even play one on TV. And you see, I'm already starting off wrong. Oh boy. Let me try my best. Something like this is what it looks like. Okay. Yeah. The calculator's my best friend when I graph these things. This one is not differentiable at x equals 0. Why? There's 0 right there. Okay. Why? Simple. Vertical tangent. That's why. It has a vertical tangent. Okay. Now let's take a look at some quick examples that we're going to run through very quickly. All right, and then we're going to give a justification as to why that's the case. So let's take a look here. We don't know what this function is, but it really doesn't matter. Where is this one not differentiable? Right there at x equal 0. So we'll say not differentiable at x equals 0. Why? A cusp. I think this is more of a corner, but we'll put both cusp or corner. Doesn't matter. I think number 7 is clearly a cusp at 0 right there. So this is actually, the same answer. Not differentiable at x equals 0. Why? A cusp or corner. Okay. So next one, last one, number 8 here. You notice this is also 0. I mean, not a big deal that they were all 0. It could move around. Don't worry. Not differentiable at x equals 0. And we're going to say why? Because it's discontinuous. You might also call it a jump. All right. But those are some good examples. It could have been at any number. Just coincidentally, all of these were 0. But I really just want you to see the difference in the way that the graph would look, because by inspecting the graph you can tell if you can take the derivative or not at a particular point. And differentiability is a big topic. I mean, the whole first semester of a Calculus 1 course is all mostly about differentiability. Okay, so I hope this video was helpful. Maybe it was longer than it needed to be, but as always, like and subscribe.